Alright guys, in this section we're going to be discussing vectors and dot products. So far you have studied two vector operations, vector addition and scalar multiplication, each of which yields another vector, right, as we saw in the previous section. In this section we're going to study a third vector operation that we call the dot product. This operation is going to yield a scalar, in other words a real number for us, rather than a vector. Instead of having a vector like we did in vector addition and scalar multiplication, we're going to get just a scalar here, which is for us a real number. Okay, so here we have the definition of dot product. Very simple, straightforward here, guys. Given two vectors here, u1, u2, and v1, v2, the dot product of u and v is equal to just the sum of the product of their components. Okay, and we represent dot product with just a bold dot there, so not to be confused with regular multiplication, because we don't have real numbers here, we have vectors. So this is analogous to multiplication operation of real numbers, but in vectors here. Okay, now instead of getting a vector, you see that our components u1, v1, u2, v2, all those are real numbers. So that operation right there is going to give you a real number. Okay, so here we have some examples to show how this process works. So we're going to find the dot product of the following vectors. So dot product of 3, 4 and 2, -3. We multiply 3 and 2 and add 4 times -3, and we have 6. And that's going to be a minus, because that negative and the plus turns into a minus 12. And we have that is equal to -6. So dot product is equal to -6 for that first problem. On the next one, the same idea. We have -3 times 1 plus -5 times -8. And again, this is just regular multiplication and addition here of real numbers. So we get -3 plus 40 is equal to -37. Okay, notice how all our answers here are real numbers, right? Not vectors. And then finally for the last one here is the same idea. We have -6 times 5 plus 5 times 6, and we're going to get -30 plus 30, and that's equal to 0. So notice how the dot product could be positive, could be negative, or could be 0. Now unlike the vector addition and scalar multiplication, we don't have an equivalent geometric representation of it, but we're going to have many real-life applications of the dot product. Here we have some properties of the dot product, and just like with multiplication of real numbers, some of these are analogous to those properties. And we have the commutative property. Dot product of 0 vector and with any vector is just 0. So that's analogous to multiplying a real number times 0. That gives us 0. And we have distributive property. And fourth one is one that is not maybe obvious at first, but it's also very straightforward. So we'll see some example of that one too. Here in this example, we're given u is equal to 3, 4, v is -2, 6, and we're asked to find each quantity here. So on the first one, we have u dot product v times, and that times is just scalar multiplication, the vector v. Notice how the dot product is going to be a scalar. So times a vector v, that's going to give us a vector at the end. So that's what you should expect. Notice here in parentheses I have the dot product of the two vectors, and I know how to calculate that now. We do 3 times -2 plus 4 times 6, and all of that times vector -2, 6. Okay, so my dot product here in brackets is equal to 18. We're going to multiply it by vector -2, 6. And we just distribute the 18, giving us a vector of -36, 108. Again, notice here how the answer is a vector. Okay, in the next problem, we have a vector dot product, another vector. Because notice how u plus v from the previous section, it's gonna give us another vector, or yields another vector. Right? So then u plus v is a vector. We're going to dot product that with vector u. Okay, so we have vector u is 3, 4, dot product, whatever that sum is, and we're going to go ahead and use our vector addition here to combine u and v, and we get 3 minus 2 is 1, 4 plus 6 is 10. So 1 comma 10 there. And now we're ready to dot product that with 3 comma 4, and that's 3 times 1 plus 4 times 10. That gives us a nice 43. Notice how the answer here is a scalar, because we ultimately are doing the dot product of two vectors. Dot product gives us a scalar there. On the previous one, we did a scalar multiplication. Right? So we have a dot product within our problem, but we ultimately doing a scalar multiplication on part A. So we're going to get a vector back. Now for the last one here, we're just finding the magnitude of V, and even though we know how to find the magnitude of V with our formula from last section, which is the square root of the first component square plus the second component square, we have V there, it is given in the problem. We're going to use here the second one, we're going to use the fourth property here just to show you how that works. Since the property says V dot product V is equal to the magnitude of V squared, so then magnitude of a vector, in this case V, is going to be equal to the square root of the dot product of the vector with itself. Just to show you that that works the same way as finding the magnitude of a vector, we can also use the dot product to find the same thing. So taking a vector, in this case V, and dot producting the vector with itself, we get negative 2 times negative 2 plus 6 times 6. So that's equivalent of saying negative 2 squared plus 6 squared, and all that under the square root. So you're going to see how we get our square root of 40, which simplified is 2 square root of 10. And there you have it. All right. So one of the applications of the dot product is going to be finding the angle between two vectors. So given vector u and v, we're sketching them in a way that they both start at the same point, at the same or initial point. We have that the angle formed by the two vectors, so we call it theta, is going to be determined by the following formula. So notice here how we have the cosine of theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Now, of course, to find the theta, you have to use the cosine inverse of that quotient, that expression on the right. So let's look at an example here to see how this process works. We're going to find the angle theta between u and v, u being 2, 1 and v 1, 3. Right? So plugging this into our equation here, we get that cosine of theta is equal to the dot product of the two vectors. So 2, 1, dot product 1, 3, all of that divided by the product of their magnitudes here. So the magnitude of u is just square root of 2 squared plus 1 squared, and then times the magnitude of v, square root of 1 squared plus 3 squared. All right, so calculating the dot product on the numerator, we get 2 times 1 plus 1 times 3, all over that magnitude there, which we have square root of 5 times the square root of 10. Okay, so this is going to be equal to 5 over square root of 5 times square root of 10 is equal to square root of 50, which, you know, simplifying it, we get square root of 50 is equal to 5 square root of 2. We can cancel out the 5 on top and bottom and get the cosine of theta is equal to 1 over the square root of 2. Now, to find theta, we're going to have to use the cosine inverse. Actually, that 1 over square root of 2 happens to be a known value from the unit circle, so we can figure this out without a calculator, but in general, that's what you'll be doing for any given value here, and that's going to be equal to pi fourths. Yeah, the nice thing about this formula is that it's not going to have any ambiguity. You don't have to worry about, you know, what quadrant the angle is going to be in. The theta, the angle between two vectors, is always going to be between 0 and 180 degrees. So it's always going to be the angle in that interval from 0 to 180 degrees. And that's what cosine inverse gives you. Okay, so here we have the definition of orthogonal vectors. And orthogonal is just a fancy word for perpendicular. So it's going to be essentially the same thing for us, right? Perpendicular just means that there is a 90-degree angle between the two vectors, right? So we have a nice definition here that says that if two vectors are orthogonal or perpendicular, if and only if the dot product of the two is equal to 0. And also if and only if means it goes the other way around. If the dot product is equal to 0, then you know the two vectors are perpendicular or orthogonal in this case. Here's an example. We'll see that. Determine whether the vectors u and v are orthogonal. And we're given u 6,10 and v -1/3, 1/5. So we're going to calculate the dot product of the two vectors and see if that gives us 0. If it does, then they're orthogonal. If it's not 0, then they're not orthogonal. Okay? So calculating the dot product, we have 6 times -1/3 plus 10 times 1/5. That's equal to -2 plus 2, which is equal to 0. Therefore, u and v are orthogonal. Okay, here we have a definition for vector components. And so given two non-zero vectors, u and v, where such that u is a sum of two other vectors, w1 and w2, where w1 and w2 are orthogonal, and w1 is parallel, or in other words, a scalar multiple of this other vector v, the vectors w1 and w2 are called the vector components of u. Now, vector w1, with the one that is right on top of vector v, is what we call the projection of u onto v, and is denoted by this PROJ for projection of u, and onto v, so it's a little v as a subscript there. Now, since u is a sum of w1 and w2, you can figure out, once you figure out w1, you can see, you can subtract that from u and figure out what w2 is. Now, notice how the projection is representing, pretend you have that u, as you see in the diagram here, and you put a light or a lamp right on top of it. The projection is really giving you the shadow of that vector onto that vector v. So that gives you that w1 there. Okay. Now, how do we find this projection? We're going to have a nice formula that uses the dot product. And again, here is another application of the dot product and to find the projection. Okay, the projection of u onto v, given these two non-zero vectors, is going to be equal to the dot product of the two divided by the magnitude of v, right? The vector you're projecting onto, square. All that multiplied by the vector v. Notice how everything here in the parentheses is a scalar, right? The dot product is a scalar, the magnitude is a scalar, so the whole thing is a scalar. In other words, a real number. So you're going to get a vector back. The projector of u onto v is a vector, right? So let's look at an example here. We're asked to find the projection of u 3,4 onto v 8,2. And then write u as a sum of two orthogonal vectors, one of which is a projection of u onto v. We're going to first start by finding the projection of u onto v by using our formula here. And we have that the projection is equal to the dot product of the two vectors, 3,4 and 8,2. All of that divided by the magnitude of v. Very important that you don't mix these two up, these two vectors. We want the magnitude of v, not u. So magnitude of v is square root of a squared plus 2 squared, and we're going to square all that. So the square is going to take care of the square root. So we're going to get 3 times 8 plus 4 times 2 on the top. All of that divided by 64 plus 4, that's 68. All right, forgot to put my v vector in here, so we're going to add the v. Right there, remember all this is being multiplied by the v, and v is 8,2. Remember the projection is going to be a vector right at the end. So we're going to calculate this whole quotient here, this expression, and multiply that scalar times our vector here. So we get 32 over 68 times our vector 8,2. Simplifying a little bit, we get 8 over 17 times our vector 8, 2, and we go ahead and distribute the scalar 8 over 17 to each component. We get the vector 64 over 17, 16 over 17. All right, so this projection is our W1. So once we have our W1, we can find W2 by subtracting this vector, W1, from U, because the idea is to write U as a sum of two orthogonal vectors. So we have W2 is equal to U minus W1, and that's going to be 3, 4 minus 64 seventeenths, 16 seventeenths, which was our W1 there. Okay, so this is just a vector addition. We're going to do the operation here, and we get W2 is going to be equal to 3 minus 64 seventeenths, gives you negative 13 over 17, comma 4 minus 16 seventeenths gives you 52 over 17. There we have our W2 vector. So then we can formally say that U is going to be equal to the sum of these two vectors, W1 and W2. Now you can verify if you've done this process correctly, W1 and W2 should be orthogonal. All right? So they're not just any two vectors, but they're two orthogonal vectors that added together gives you this vector U. We're not going to verify it, but you could verify it by just doing the dot product of the two, W1 and W2, and see that that's actually 0, proving that they're in fact orthogonal. So there we have it. Another application of the dot product and projections is going to be work. And the work is, we're going to call it W, done by a constant force F acting along the line motion of an object is given, acting along the line of motion of an object is given by the formula force times distance, okay? Or the magnitude of the force times the distance traveled by this object. And this formula is applied when the force is parallel to the vector PQ. This case, which represents the ground here, the surface where this object is moving. Okay, but what happens when we have a force that is not parallel to that vector or to the ground or to the surface there, and we have instead a force that forms an angle with the horizontal, and we call that angle theta. Well, to be able to use the formula that we had here above, we're going to need that horizontal component of that force. In other words, the projection of the force vector F onto the vector PQ. So rewriting our formula there, instead of using the magnitude of the force there, since it is at an angle, we're going to use the projection of that force onto PQ times the distance, which is the magnitude of PQ. Now, of course, that projection can also be written, and we can use a little bit of a trig here to write the projection, or the magnitude of the projection, I should say, because remember the projection is a vector. Projection of F onto PQ is a vector itself, but we're taking the magnitude of it. That's going to be equal to the cosine of the angle formed with the horizontal, cosine of theta times the magnitude of the force, right? And you can just use your basic trigonometry to prove that, giving us now another form of writing the work formula as the dot product of the force vector with the distance vector, which is PQ in this instance. So we have a projection form and a dot product form. Let's look at an example here to see how this process works. And you can use either form, just depending on what's easiest and what's given in the problem. We have a person pulls a wagon by exerting a constant force of 35 pounds on a handle that makes a 30-degree angle with the horizontal. Determine the work done in pulling the wagon 40 feet. Okay, notice here we have roughly a picture of what's going on. Just pulling this wagon here with that force. The force that's at an angle here, 30 degrees with the horizontal, and the distance you're going to move it is 40 feet, right? We want to determine the work done. So here is convenient, since we have the angle, to use the cosine of theta here. So that second line of our formula there. Okay, so now we're using the projection. Instead of using the dot product form, since we don't have the component forms or the representations of the vectors here. We have magnitudes. It's easiest to just use the projection form, which translates into cosine of theta, of the angle, with the horizontal, which is cosine of 30 degrees, times the magnitude of the fourth, which is given by the problem already, it's 35 pounds, times the magnitude of the vector PQ, which is distance for us. Okay, it's 40 feet. So putting that in the calculator, evaluating cosine of 30 degrees times 35 times 40 gives you approximately 1,212.4 foot-pounds. So this is going to be our units for work. All right, and there we have it.